All right, welcome back, everybody. With your 3-day weekend, it's time to jump back into it. Gonna go over the calendar real quick, but before you know it, midterm's gonna be here. Okay, so notice we're here on the 18th. Today, we're gonna finish up 4-4, probably get into 4-5. We'll see. The next day, gonna be the 20th. We're gonna go ahead and start on 5-1 and then 5-2. I'll do a midterm review and then notice on right here. March 4th will be your midterm. Okay, so it's exactly 2 weeks from today is your midterm. And then, of course, don't forget, it's on here in your calendar. I will send out an announcement that there's no class on Thursday the 6th. I'll be gone to the convention that day. Okay, so if you're behind, get caught up. If you have any questions, please feel free to reach out. Chapter 5, we only go over 5-1 and 5-2, so don't worry too much about that. A lot of calculator work in 5-1 and 5-2, so don't stress out too much. But like I said, we will go over we'll have a little midterm review. I'll go over a few questions with you and stuff like that, okay? It'll be on your computer, just like you did the last quiz, but it'll be randomized, okay? So you don't know which question you're gonna get. I've got a question bank on each single one, so. Makes it good, just same as before. Make sure to bring your calculator. If you still don't have a calculator, get one. You're definitely gonna need one by chapter 5. Okay? Because you don't want to, first time I don't show you the formulas on that one. You're just gonna have to know how to do it on your calculator. Okay. Good so far? Good? All right. Let's do just some quick little verbal review, so it might behoove you to answer me. Because it's gonna help you because I'm gonna start trying to remind you of stuff now. Do we remember what sigma is? Yeah, do this. That, okay. What is it?
Standard deviation.
Very good. Standard deviation. Here's a little hint, because I have given you enough time to be in class now. If you don't talk, I don't think you need review. So then I just won't review you. And then you may God have mercy on your soul on the midterm. Okay. So what about this right here? And it doesn't need to be the same people answering either. Mu, very good. What does mu mean? Mean, I got, what's that? Population, y'all were good about means, but don't forget population mean, okay? So right here with population mean. How about this one right here? What is that? Z-score, do we remember? Just give me, remember they're both basically roughly the same. Let's do the population one. What would be the population one?
X minus X bar.
Minus mu. I don't know.
Yep, you had it, mu. X bars are sample, remember? Okay. Technically the same. Are we all technically the same, depending, but we got to think about context in this class. I really want you to start thinking about context, because after midterm, that's when things they don't get hard, guys. They just get a little bit more abstract, okay? Because we're going to move away from the population we've been dealing with, and then we start doing samples. That's when we're actually going to start. I always say this statistics class starts after midterm. Okay. Okay, what goes on the bottom?
Sigma.
Very good, sigma. What does it mean?
The distance between
You were close. You had it right on distance. Distance from mean, exactly. The exact distance from the mean, okay? Notice, because remember, you had those standard deviations. One standard deviation was what?
60.
58, exactly. 2 standard deviations?
95.
Very good. 3 standard deviations?
99.7.
Very good. Will that be on your midterm?
Probably.
Might be, okay? But notice that's in a perfect world if everything is in 1, 2, 3 plus or minus. But in the real world, what's going to happen? Things are going to be kind of in there, not exactly. Okay, so we kind of want to remember that. And that's what the z-score tells us. So we can just put distance plus or minus from the mean. It really means a little bit more than that, but I don't want to start muddying the water too much. Okay. The young lady over there says something. What is X bar?
Sample means.
Sample mean. Very good. Notice we could always write another z-score if we wanted to with this one, with the sample mean, couldn't we? I would just put x minus x bar, but now what do I put? S, exactly. I don't use the sigma notation anymore because how do we know the difference between population and samples? Greek and everything else, right? Now, that kind of breaks the rule here, thinking of the Z and stuff like that, but still, at least in the formula, I can kind of see some Greek letters in there. So yes, this will be a S. What is this one?
Population variance.
Very good. Population variance. Okay, so if this is population variance, how would I get my sigma?
Just square root.
Square root, exactly. Now, does your calculator give you variance? No, what do you have to do?
Square it.
Square it. Okay, good so far. Now, on your calculator, does it give you just one type of standard deviation? No, remember, there's a sigma that you could look at, right? Then right above that, there's a S. So you got to be careful, okay, later on, which one do you need to look at? Do you need to look at the population mean or do you need to look at the sample mean? That only comes from like looking at the question, okay? So far, so good? Kind of good review on that, just a little bit, kind of remembering stuff. Overall, the biggest part I saw on the last empirical quiz was honestly just do a little bit more study. Okay, especially about those like distances and stuff like that. Let me think. When you see this, what rule am I going to use?
Addition.
How do you know?
Or.
Look for the or. Okay, that guy right there says, hey, if I'm trying to take a probability, it says, what is the probability of this or this? It's going to be addition rule, which we know looks like this. The probability of E plus the probability of F. Now, let me ask you another question. Technically speaking, when I first taught you this, you saw this, the minus the probability of E and F. When would I not need this part?
And then.
When there's no crossover?
I like that. Give me the word. He's right. He's 100% right, but give me the word I used. Mutually exclusive. When you're dealing with mutually exclusive events, okay, remember what that is. Mutually exclusive means they can't happen at the same time. That's like, can I flip a coin and get a heads and a tails? That can't happen. You know, I can't draw a black card and a red card. I'm either going to draw a black, you know, or red. That's it. So you got to look for that. Okay. Now, if they're not mutually exclusive, then I've got to get rid of that intersection because remember, this is saying this. If you've got two events, you got to get rid of the intersection. That's what that guy in this part means. Intersection. Good so far? Kind of kicking off some cobwebs over your 3-day weekend a little bit, okay? Disappointment from Valentine's Day. Remember now. How about this one? What does this one say? P, E, and F. First off, let me ask you a question. Is this an intersection? Let's walk it back. First off, I taught you the additional, right? The specific word I told you to look for that you all just told me was the or. Okay. We also need to know, is it a mutually exclusive event? If it is a mutually exclusive, we don't got to worry about that intersection because there can't be one. We just take this probability, add it to this probability, and we are good to go. Okay, but then I taught you what? What's the next rule? Multiplication rule, exactly. Okay. Did I tell you to look for an and? In fact, I actually said to you, you need to say what?
And then.
Yes, this right here, this is the probability of E, and then the next thing happening, okay? So, and then that happening, okay? Kind of remember that now? Remember the rubber duckies? Okay, we had two examples in this. We had with replacement and without replacement. There was a special word. Okay, so when it's with replacement, right, what do we call that? Starts with I, independent events. Because for it to be an independent event, now remember, that is not the same as mutually exclusive. Mutually exclusive says what? This can't happen at the same time as this. It's impossible, can't work. Independent says this, hey, this probability happened. And it has no bearing on this probability at all. If a young lady has a kid, she's either going to have a boy or a girl. She has that baby. And until science comes out and tells us differently, when she has her next child, this first thing happening had no effect on her having a boy or a girl for the second time. Okay? It's 50-50 here. It's 50-50 here. There was no effect. Or like flipping a coin. I flip a coin, I get a heads. Do you think while I'm flipping that coin, that coin goes, I already got a heads. I better make this a tails this time. No, the coin there's no bearing on what happens. Okay? So think about independent events. What would be a dependent event? We use the other word for that. Well, think about it. If I put with replacement, right? That was like this. You draw a deck of cards. With replacement, sorry. You draw a card. What'd you do to the card? You put it back. When we did the duck experiment, what did we do? I picked the duck out, I looked, and then I did what? I put it back in. But what was the other thing? I kept it. Remember? I took the duck out. I changed the size of my universe. My universe no longer had 50 ducks, it now had 49 ducks. So that changed our universe size. And if you remember back to that example, it actually made our probability worse. It's kind of unintuitive. We think it would make it better but it actually made it worse. Remember, I think one was like 0.36%, but then without replacement became like 0.24%. Okay. Got to remember that kind of stuff. Okay, good. Kind of remember some of this now. I get it. You haven't done a lot of it, but it's kind of good little review. Okay. You also saw it like this one. The probability of F given E. This is the first trial. This is the second trial. Remember, that formula goes the probability of E times the probability of F given E. Okay? Remember, that F given E is exactly what you did. That's a dependent event. The probability of me getting a duck, there's 3 stars out of 50. It's going to be 3 out of 50. I draw them. Well, now the next probability, the probability of F, given that E has already happened, all it's saying is I have changed my universe because this probability has affected this new one. Okay? Is now going to be what? 2/49 because things have changed. I have changed the universe size. Okay? So I have changed the amount of outcomes. Are we good? Quick, I know it's a kind of a quick review, but does it help kick off some cobwebs a little bit, especially maybe about the standard deviations. How many of y'all thought we were done with those? Oh, no, they're coming back. Okay. Good? All right, let's jump in. Am I an email away if you have any questions? We go to the calendar. Everybody see it? Okay. Just remember, like I said, the midterm will be on Tuesday, the 4th. If you miss the test, you will have till Friday at noon to take it in the testing center. Or if you're in one of the proctor sites, you have to take it with your proctor in class. And I do give you all class for that. Okay, so it's, like I said, you can use scratch paper, you can use your calendar. Okay, now it is the final that I will give you a list of formulas. Okay, not the midterm. Okay, the midterm is literally just come with what you know, can't use notes, can't use note cards. Okay, good. Okay. I always want to be transparent. So today, we are getting into combinations and permutations. Do you remember the final example I kind of showed you there toward the end of class the other day? Where it was like, hey, if you want to find out all the outcomes of something, of like certain trials, like, remember the one I used this, I think it was the class one. Person's gonna take a class, right? And they have like so many of this class, like 12 college algebra to choose from. XY, so many different classes. How many different ways could she have a schedule, or he, or whoever it was? I think they had like a weird name. And all we did was we multiplied those together, right? We said, hey, this times this times this times this. Okay, I showed you on a little tree diagram how that kind of related back to that quarter thing. How you can go, hey, this, if it heads or tails, from here, you can go heads or tails or heads or tails. That's how it kind of related. This is where we kind of lead into this. This is combinations and permutations. For some of you, it's going to click immediately. Congratulations for those of you, probably 90% of you. Me, I was so stupid at this for a long time. It for some reason, my brain just could not grasp it just right. And even now, whenever you get into like upper level combinations, permutations, it can feel a little bit, just being blunt and honest, probabilities are not something we as humans intuitively understand just easily, because you can tell me the number 5 and I'm like, I got you. You can even tell me 5 times 5. I can even do like, quadratic form. I go, I can get that, it's messy, but I get it. Probabilities though, they go against my preconceived notions of how I think sometimes the world should work. Okay. So let me show you. Let me make sure my pen is working. Okay, combinations and permutations. Once again, there's an operative thing I'm going to tell you to kind of watch out for. And if you start listening to me very carefully in this class, I'm always going to be tossing out these little breadcrumbs that says, hey, if you watch for this, whatever this may be, it automatically tells you what to look for. Okay, i.e., mu, Greek, population. Okay, that's at least narrowed the field, didn't it? You're not having to look at everything. You've narrowed the field a little bit. So kind of going with that. So what are combinations and permutations? Well, let's get past some new terminology for you. You may have not seen this mathematical symbol before. Okay, this is called a factorial. Okay, it has a exclamation mark. I'm not going to be proving this to you. This is sort of one of those, hey, just trust your math teacher kind of thing. Okay, but also when you see a factorial, if you see something called 0 factorial, that equals 1. You're going to need to know that. Okay, 0 factorial is 1. Now, what is it really? They grow really, really quick. Okay, first off, let me give you an example of one. Let's say I have n is equal to 6. If you look at the formula and start playing with the formula, realize what's going to happen. You can plug in the 6 into the formula, and it'll make the formula seem more like, oh, I get what it's doing. But let me show you really what it's doing. When you have n equals 6, the factorial of this is going to turn into, well, let's do this. 6 times 5 times 4 times 3 times 2 times 1. That's what a factorial does. It says whatever n I give you, we're going to start multiplying down. So 6, 5, 4, we just have a countdown. That's all we're doing. And we multiply all of those together. When we do that, we get 720. Note, factorials grow quickly. How quickly? You want a mathematical fact? I always, when my daughter, sometimes she'll say, I just don't feel like I've ever done anything unique. And when I did this to her the first time, I'll be honest, I got a really, really mean look from her. But then later on, she came back and went, Dad, that's kind of cool. But if, and this is where I kind of get humble. I get humbled by a lot of things, like reading my Bible, but also math humbles me because I start realizing how small I am sometimes. But if you want to do something unique in your life, go home and shuffle a deck of cards. I know you're thinking, what? What do you mean shuffle a deck of cards? Well, what it says is this. Now think about it. How many combinations could there possibly be in a deck of cards? Well, isn't there 52 cards? Well, to find every combination, what did I just teach you? On trial 1, there's 52, then 51, then 50, then 49, then 48. Notice what I'm doing. I'm using that fundamental counting principle. When you actually do all the math to that, and I think you can do it on you can't do it on some calculators. I think you can do it on your computer. You can put in 52 factorial. There are more combinations. Basically, there's more ways to shuffle a deck of cards than there are atoms in the observable universe. Atoms in the observable universe. That means when you go shuffle a deck of cards, it is almost infinitely probabilistic that someone has done that exact same shuffle. And so therefore, you've done something that no other human has ever done, ever. And matter of fact, for you to get the same shuffle as someone else, every person on Earth would have to shuffle a deck every second for something like 10,000 years. Okay? Before there would finally be a repeat. Kind of insane. So when you start feeling, yeah, I know it's kind of blows your mind. You're like just off of a deck of cards. Okay? Good news. These numbers get large really quickly. Better news. You have a button on your calculator. Okay? So let me tell you where it's at. You're going to go to your calculator. Oh, do you have it? You're going to go to math. Then you're going to have to scroll because once you hit the math key, you're going to have to scroll past some things. Okay? And you're going to go to probability. Okay? And then notice there is a exclamation key. Okay, that means you need to put the number in first, just so you know. Okay? Let me kind of. Here, notice, I'll show you my calculator so you have it. Let's once again, I'll do the 6 factorial. I got 6 here. I'm going to come over here and hit math. Notice I scroll over here to probability and look right here. Look at number 4. And it should be number 4 on everybody's. It doesn't matter what, if you've got a Texas Instrument, TI, it should be number 4. Am I correct on that with everybody? Okay. Once you hit enter, there you go. Notice it just put a exclamation point. I'm looking at it and I'm wanting to call it an exclamation point, but it's a factorial. Okay. Once you hit enter, look what we get. There you go. We can always check. Let's see what's 52 factorial. Not math. Well, there you go. Scientific notation says that is 8 point. Then you have to move that decimal place if you did 52 factorial, 67 places to the right. So that is 8 with 67 place values. That's how many different combinations there are.
Is there any way you can make it a little bigger? It's a little hard to see.
I can. Let's see. Cool. Is that better there?
Yes.
So you go, once again, hit your math key. Let's do it again. I'll just do the 6 again. I got a 6 here. Hit your math key. It's gonna be right beneath your green alpha key. Okay. Hit math. Notice you got a whole bunch. You got math, numbers, complex. Okay, some of y'all might not have that one, but you do have probability right there. Okay. Scroll down to number 4 or hit number 4, whichever you want to do. Hit enter again, you get to 720. And yes, you can do mathematical operations with this as well. Okay, you can come in here, look carefully. I can come in here and do this. I always use parentheses. It might not be necessary. I am a parentheses snob. But you're gonna have some questions on your homework and possibly even on your midterm. I don't know. It may look like this. I may have you dividing factorials. So I would come here, put a parenthesis, hit like say 9. Math. Oops, sorry. 9. Divided by 8. Notice I'm just dividing one factorial by another factorial. Okay. And I get 9. Okay. I can show you why that works, but if you think about it, when you think about what a factorial is, look at why that worked. What is a 9 factorial? But isn't that just 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? And I did that what? Divided by 8, right? Well, isn't that just 8 times 7 times ... 2 times 1? Aren't we dealing with just fractions still? So wouldn't like that cancel? You know, wouldn't all of this be on there cancel? And wouldn't that cancel as well? That's why we just got a 9. See how that kind of works? That's going to help out because sometimes your calculator is fast, but believe it or not, you are faster sometimes. Okay, does that kind of help y'all see that? Okay, let's jump in. We understand factorials. Let's get into combinations and permutations. I really wanted to make sure you had a really good understanding of factorial. You still have not learned what a combination or a permutation is. Combination, definition. Combination is a selection of objects from a group without regard to their arrangement. Okay? You are gonna want to remember this. I promise you. Because there's a big difference between combination and permutation. Okay? You will get 2 totally different answers, and I don't give a lot of partials on it. Easier way to remember it is look here. Right there. Combination. Order does not matter. Permutation. Order matters. Hopefully you noticed. Okay. When you went to your math key, did you notice, did you see something now? And I'll show you shortly. Right there, how you got to that factorial, there's buttons that do this as well. They will do combinations for you. They will do permutations for you. Some examples of combinations. Well, depends on who you are, but how about friends? If you're going to line up your friends, does order matter? Maybe not. Maybe it does. Think about yourself. How about ingredients? Pizza toppings. I always say order doesn't matter as long as it comes after the cheese. Am I right about that? Would you really want to eat a pizza where all the good stuff is like underneath the cheese? I don't know. It would taste exactly the same. Let's be honest. But in your mind, it wouldn't. You'd be like, that pizza sucks. I don't know what they did there. Once again, you can use your calculator. Okay. Your calculator is going to look like this. Once again, you're going to use your math key. Then you're going to go once again to probability. And you're going to look for this symbol. N choose R. Permutations. Order matters. Okay? Example for those. How about a combination lock? Letters in a word. Kind of makes sense. Letters in a word, they gotta be in a certain order. To get to it, once again, you will use your calculator. You can use your math. Go to probability. And then you will look for N, P, R. The NC, we can always say N choose R. That's sort of my thing. The NP, you say N pick, but really, I always say permutation on that one because I want to make sure that I understand the combination. Order doesn't matter. Okay? Permutation. Order matters. For any of you future computer science people, think of what a computer does. It does permutations. Order matters. A computer says, I need to do this, I need to do this, I need to do this, I need to do this. The computer can't go, I'll do whatever I want in whatever order I want. I've got to do it in a certain order. Well, that's a permutation. Order matters. Okay, permutations. Good so far? Look at the examples. So some examples of permutations. Here we are. I did this at the Pleta bar. I went to the Pleta bar one day and I was like, I wonder how many combinations there are of this. Because I know what they say on their advertisement. They're wrong. And I figured it out. Okay. It's like 6.7 billion different combinations you can get on stuff. Okay. But order doesn't matter. Okay. So once again, pizza toppings, sandwiches, lottery. Order doesn't matter. For those of you who play the lottery, hopefully none of you. Consider that a cafeteria is serving vegetables for lunch one day, for one weekend. But they have carrots, green beans, lima beans, celery, corn, broccoli, and spinach. Okay, notice they gave you an amount of stuff. Okay? Suppose now that Bill wishes to order a vegetable plate with 3 different vegetables. How many ways can his plate be prepared? Notice what it's saying. Does order matter? No. We're doing combination. Order doesn't matter. How many things do we have to choose from? 7. Okay. Well, good. First off, you need to decide one, does order matter? No. Good. Okay, since it doesn't matter, we can either use our calculator or I'll show you the formula shortly. But notice we have an N. We know that there are 7 possible things we can choose from. So what's my R? What's my amount of choices? 3, exactly. So my R is going to equal 3. And so my N choose R. Now, this is how you put it in your calculator. You got to put the 7 first. Okay? So you come put the 7, and then you go ahead and hit your math key. Then you go and hit your probability key. And then you go find the N choose R key. That's what you're looking for. N choose R. It's going to throw that down for you. In some cases, it's going to give you a little box to put a 7 in. And the TI-83, it's just going to have the 7, and then it's going to have the N choose R, and then you need to put the 3 down. And then we put the 3. Later on, you're going to see me write this way. I tend to go back and forth. You're either going to see 7, choose 3, or you'll see this, 7, 3. That is not a fraction. Okay? That says 7, choose 3. And does anybody have a number for it? Very good. So there are 35 different combinations. Just with 7 ingredients. Okay? That's going to become, once again, very important moving forward. Okay, it'll be something I reference later. Okay. I'll say, hey, don't forget, we gotta find the combinations of this, okay? And so we have to go back into our calculator and pull it out, okay? I will remind you, but it is gonna be one of those things. This is the section where things start to get a little bit more abstract, okay? Usually the part where I start getting a lot of like the weird emos going, man, I was great until chapter 5. And then all of a sudden, it's like, I woke up and I was in a brand new class, okay? So I want you to stay with me, okay? Permutation. A selection of objects from a group where arrangement is specific, i.e. a lock. A race. Order kind of matters, don't you think, in a race? Like there's first, second, third, fourth, yes. Well, would order matter in this situation if you were going to be picking a bridesmaid? Probably. You know, you're going to pick a bridesmaid or something like that, yeah. You can only have technically like, what is it? Who's the head bridesmaid? What do they call that person? Maid of honor, new ladies. Look how quick they knew, guys. Remember that for later. Okay. And then it goes down from there. And order probably matters because one girl's gonna go, why wasn't I the second choice? Why wasn't I for the first choice? So order matters. Permutation. Concerts. Order matters. You know what I mean? I'll be honest, I'm kind of a nerd. I don't like staying up late. So if I want to go to a concert, if the band I want to see plays early, I'll go. If the band plays late, I don't want to go. But order matters. Okay. Also, maybe in how you pay them. So let's look at an example. Why would order matter? Think of one of the last questions I showed you in the last class. Remember when we were picking the VP and everybody else like that? Well, what you don't realize is you were actually doing a permutation. Okay. So a class of 18 fifth graders is holding elections for class president, vice president, and secretary. In how many different ways can the officers be elected? Well, now let's think about it. Let's think. Remember, if we were back in chapter 4, I would have said, okay, how many ways is there to pick a president? How many people do I have to choose from? Very good. I have 18 people. Okay, so we do our thing, we pick our president. And then what? Now we got to pick our VP. So now how many people do we have to pick? Because remember, we've already picked the president. We can't have a president be a president and a vice president, can we? That wouldn't make sense. So now how many people do we have to pick from?
17.
Exactly, 17. And now we got to pick a secretary. Now how many people do we have left? 16. And then we can do the math of that very easily. Do 18 times 17 times 16, and we get 4,896. Did order matter? Yeah, order did matter. There's a big difference between president, vice president, and secretary. Trust me. Okay. Once again, there's two other ways to do this one. I'm going to show you this. One, your calculator. Same process as before. Use your calculator. You're going to want to go ahead and put in, how many people do we have to choose from? 18. So you're going to want to put the 18 first. And then you're going to want to go back to your math. Probability. And then we're looking for what? NPR. We're looking for a permutation now. What is my R? Exactly, 3. 3 positions, president, vice president, secretary, 3 positions. So then we put in a 3, and you should get, once again, 4,896. So that's a way to do it. Okay? Or now showing you the, and I'll show you both formulas here in just a second. Notice you can use the formula if you choose to, which sometimes is easier. You can come here and go, hey, NPR looks like this. Remember, is N factorial divided by N minus R factorial. Okay, and that's it. Okay, so notice you could come in here and do this. 18 factorial, well, hey, what's 18 minus 3?
50.
What is it? Statistics students? 15, thank you. 15 factorial. Can we all agree that I could actually write this as 18 times 17 times 16 times 15 dot, right? And then the bottom's just gonna be what? 15 times dot. Doesn't everything from there cancel? And then we're just left with that. And so once again, that will turn into 4,890. Three different ways to do it. Seeing all the formulas, there they are. When order is not important, the following formula is used to calculate the number of commutations. N choose R, okay, is equal to n factorial all over n minus r factorial times r factorial. The r factorial, that guy on the outside, it's getting rid of some extraneous solution, okay? Because remember, with combinations, order doesn't matter. I could give you like, say, 1, 2 or 2, 1. Order didn't matter. Whereas with permutations, that 1, 2 and 2, 1 are the same to it because it says, I can't have that. I need to just get those. I need to get rid of any extras out. That's why there's that extra r factorial, okay, on the choose. When order is important, the following formula for the other one I just showed you, n permutates r is n choose r divided by n minus r. Okay. The thing below there is just some ways you may see it. I do tend to use for combinations because we're going to be using it a lot. Combinations we use a lot. I tend to use this guy a whole bunch. Okay. This one sort of, but the bottom one a lot. They mean the exact same thing. It just really depends on your textbook. Might be going to a different textbook. Don't know when. But there you go. Permutation, I'll be honest, I've really never seen, I don't see this very often. And I don't see this very often. And I've only seen that once. Okay, so really, for permutation, that's what you're gonna see. Okay, but notice there's not like a fraction looking one for the permutation. Okay, don't have that. The only one that looks like a fraction is the n choose r, but it's missing the bar. Okay. So, n, number of items in the set. R, number of selected items. Are we good so far? Kind of got it, more or less. Let me show you some special permutations. Special permutations involve objects that are identical. Okay, the number of distinguishable permutations. Distinguishable permutations of n are objects of which k sub 1 are all alike, k sub 2 are all alike, and so on and so forth. So basically it's saying, hey, your little k sub 1, instead of just multiplying everything to itself, I gotta go, where does this match? That's my grouping of all my matches for that guy. How many match here? There's that guy. How many match here? There's that guy. Notice, in how many different ways can you arrange the letters in the word Tennessee? This might be a midterm question. just not Tennessee. Well, first off, group your letters. Okay, first off, how many different types of letters are there? Well, I see a T, an E, an N, and an S. So good on that? So notice, I created 4 groups. Those are the letters I'm using to create Tennessee. Now I need to go there and count how many of each occurrence I see of each term, okay? So notice with the T is a 1. Okay, the E, and how I used to do this is like, notice, I kind of scratch it out. E, well, let's go here. I got 1, 2, 3, 4. So that gives me 1, 2, 3, 4. Well, that's going to give me a 4. N's 1, 2. There's it, 2. And then the S's 1, 2. Here's a little helpful hint. 1 plus 4 plus 2 plus 2. Well, 4 plus 4, it's going to give me 9. Make sure there's 9 right there. It's really easy to miscount. And when you miscount in math, you get the wrong answer. Okay? So notice what this is saying now. I can find out, well, what's all the possible arrangements? I can look at my formula that says, hey, how about we do this? We know all the possible choices are 9. That is the total letters. So that's going to be a 9 factorial on top. All divided by, well, do it this way. 1 factorial times 4 factorial times 2 factorial, okay, times 2 factorial. Lots of different ways to do this. And first off, to be honest, 1 factorial, you really don't need because that's multiplying everything by what? 1. So I really don't need him. So then I could come in here and do this. I could go 9 times 8 times 7 times 6 times 2. Sorry, 7. That worked. And went to the 2 all of a sudden. Times 5, 4, 3, 2, and 1. All over. Well, notice 4 times 3 times 2 times 1. Right? Well, can we all agree with that part? All of that goes away. But then I have what? 2 times 1. And then I have what? 2 times 1. Because I have these guys right there left. All these other parts got reduced down. Well, 2 times 1 is just 2. So 2 times 2, that's just going to end up being all of that top 9, 8, 7, 6, 5 divided by 4. When you do it, I would do it on my calculator, and you could put it in exactly like this. It does get annoying because you're having to go in there and go, ugh, got to go back, hit the math key, scroll over, hit it, you know. But when you do this, your final answer is going to be there's 3,780 different ways to arrange those letters. Okay. Notice it's permutation. That means to arrange the letters in a specific order. That does not mean that you're creating, that doesn't say there's 3,780 different words that I can create out of the word Tennessee. It's just how to arrange those letters. Okay, that's it. Okay, so kind of remember that. Having said that, you saw how I did that one. Do that. And I'll give you a minute. Eight. Eight. Keep working on it, play catch up. If you're gonna going along with my method here. Get there. Might have gotten to see. Remember our formula, we got n factorial all over k1 factorial times k sub 2 factorial times k sub n factorial. N just means whatever number you're stopping at, whatever n number you have. We notice we have an n number. How many words are in the word? How many letters are in the word Missouri? We know our n is equal to 8. That's how many groups we have, but still. So notice we can write this down. You can do this on your calculator, or you can use a formula. You got 8 times 7 times 6 times 5, 4, 3, 2, 1. All over. Well, notice I have 1 factorial times 2 factorial times 2 factorial times 1 factorial times 1 factorial times 1 factorial. Can we all agree that I really don't need the 1 factorials? Because you really don't have to multiply by 1, so all of these guys can just go away completely, okay? And even if you really wanted to, you could go ahead and take away a 1 at the top, because it does nothing really. Matter of fact, some statistic books even don't even show the 1 part of the factorial anymore. I'm not one of those who agree with that. This turns into 8, 7, 6, 5, 4, 3, 2 all over 2 times 1, 2 times 1, because of my other factorials left, right? Notice this guy's going to go away with that. And so you're literally just left with 8, 7, 6, 5, 4, 3, all divided by 2. And my man is correct. When you do the math, you get 10,080. I did it the long way. You can use your calculator, which is 100% A-OK to do, okay? Just to be blunt and honest, you're not getting any special points because you showed me how you can do a formula, okay? I am much more concerned with, can you do it correctly, and can you actually tell me, like, what is this saying, okay? That will be some questions that you will probably see on your final, is to kind of finish off the question. Like, you may do the math perfectly, but then I'm gonna say to you, now tell me what you're seeing. Okay, so 5 points get you the perfect math, but the other 5 points says this: I listened enough in class to remember what I was told about what I just did. And that's where it kind of flops people a little bit. Okay. For example, think about your last test. When I said to you, what was a standard deviation? Okay. You need to have a password with 6 letters followed by 2 odd digits between 0 and 9 inclusive. Inclusive, you want to write this down because I will not answer an email. Inclusive means you have to add the endpoints. You have to include those into it, okay? Now that it's set on class, and it will be on YouTube. There you go, there it is. Okay, So you have to, inclusive means the endpoints have to be included. Exclusive means you don't add the endpoints. Okay, you've seen this before. If I showed you 0,9 back in intermediate algebra, you should have said that can include 0 and 9 because I'm using brackets. Whereas if I said 0,9, guess what? I can't include 0 and 9 because I'm using parentheses. That means I can get infinitely close to 0 or infinitely close to 9, but I can never equal them. So that's kind of what that means when you see the word inclusive. Okay. If the characters and digits cannot be used more than once, how many choices do you have for your password? What do you think we're using? Are we going to be using combinations or permutations? Why?
Because it has to be in order.
Has to be in order. Does order matters, doesn't it? Because it is a combination. If order didn't matter, I could break into every single one of your computers, you name it, your bank accounts. But order matters. So let's think about this. How many things, okay, do we have to choose from?
Six letters.
Followed by what?
2 digits.
2 digits. Okay, well, let's think about this. I need to have a password with 6 letters. How many letters are there? 26 letters. How many am I allowed to choose from? Is that it though?
No.
Now what do I have to do?
2 digits.
2 what?
Odd.
Odd digits. How many odd digits are there?
Two.
What'd you say?
5.
5. Does 0 count?
Yes.
Is 0 even or odd?
Oh.
You ever thought about that? To hear somebody listen, just go, oh my gosh, what? It's an even number. 0 is considered. Technically, we consider it even. Okay, let's call it non-negative. So yes, we do have 5. But how many can we pick out of those odds? 2. Do the math of that. And yes, you can put it in your calculator that way. I would probably do it this way. Parenthesis here. Parenthesis there. That way everything's kind of contained, but that's my personal thoughts on the matter. When you calculate your first number, notice, and I'm hearing a lot of talk back there that I'm gonna get really tired of pretty fast. It only has to happen. It's about the second time, so I might be moving people around. So notice when you do your 26 permutation 6, you get 1, 6, 5, 7, 6, 5, 6, 0, 0, which is just a massively large 165,765,600 times 20. Which gives you how many possible passwords could there possibly be just with this? Exactly. So just with choosing 6 letters followed by 2 odd numbers, you have 3,315,312,000 different possible permutations of that, which is insane. For us, you can't do it. Okay. Here's a little bit of numeracy for you. About 1 week is 1,000,000 seconds. Okay. Do you know how long 1,000,000,000 seconds is? Pretty close, 30 years. Notice the difference in numbers, okay? So you will never reach, if you try to calculate all the 3 billion different permutations we have up there of that. Now, the reason why your computers will say, please give me this many, and then all this stuff is because a computer could do that in about 10 minutes. Okay? But there are things that go out there exponentially and make it very, very large. Good on this? All right, I'm gonna jump into 4.5. 4.5, I'm not really gonna teach you because there's nothing to teach. As a matter of fact, there's not even gonna be a video on it. Because it literally says, hey, all this probability stuff you've learned with permutations, combinations, addition, and multiplication, we're gonna turn it all into just one lesson. Okay? It's sort of like your old school word problems that you saw back in college algebra. Okay, so that's all it really is. It just, and I've got some examples in there. Okay, so let's just do a couple of examples, and that way next few classes we can deal with chapter 5. Like I said, I got about, I want to say, for these 2, 3, 4. I got 3. Well, about, I think I got more than that. 1, 2. There's a few examples on here, so it'll be good. Biggest thing you're gonna start remembering is this is going to become very important for your moving forward, is seeing those terms. Everything from here on out, well, I'm gonna be saying a lot. At least, at most, greater than, less than, between. Okay? Matter of fact, whenever we get to chapter 5.1 and 5.2, the difference between two of those words is the difference between whether you use this button on your calculator or this button on your calculator. Okay? Tony wants to buy a new car for each of his 2 cats. The collars come in a choice of 8 colors. How many selections of collars for the 2 cats are possible if, what did it just say? Repetitions are allowed. So, what am I using? Combination. Now, here's the problem. You're probably going to try to do something like, 8 choose 2 or something like that. Okay? Might work, never tried it. But realize you're using a counting principle. Okay, how many choices for the first cat do we have?
8.
Okay. How many choices for the second cat?
8.
What's 8 times 8?
64.
I was getting worried. There's your answer. Good. Could you have used the combination? Yeah. Could have, but that was just counting principle there. Okay. Now, how did I know? First off, it's talking about choices. Okay. I want to buy a new collar for each of the 2. The collars came in a choice of 8 colors. And then it told me you're using choices. So I know in my brain, I'm gonna have to go to one of 3 things. Counting principle, which is quick. Obviously, this times this. Combinations, which means what? Does order matter? No. Does it matter for my cats? No. So there's where I stop. I don't need to go to permit. Now, if order did matter, like I had a finicky cat, maybe, but didn't matter in this one. Good? Okay. Well, what about this one though? Tony wants to buy a new collar. Same question, but what did they change? So how many choices do I have for my first cat? You still have 8, right? First cat. But how many choices now do I have for my second cat?
7.
7. And what's 8 times 7?
56.
Very good. So there's 56. 56 what?
Selection.
Very good. Different selections. Exactly. different selections. Different combinations, exactly, but without repetition, because I gave the first cat a red collar. Well, if you have two cats that look exactly the same, it'd be kind of weird to give them both a red collar. So might go with the second one if I was gonna do this. So different. Let me see if there's a harder one on here real quick, because I wonder if there's any. Let me skip and I'll do one more for you, then we'll be done for the day. And this will finish us up with chapter 4. I do believe, correct me if I'm wrong, this will open up, no, they're the chapter 4-5 test, not chapter 4 test, am I correct? I think it's chapter 4-5 test. You should go. Let's do this right here. How many possible ways can a person toss a coin 10 times so that the number of tails is between 5 and 8? What does it say? Inclusively. So therefore, do I need to include the 5 and the 8?
Yes.
Yes. How many ways? Put it this way, how many trials are there? 10. Am I using permutation or am I using combination?
Combinations.
Combination. Or it doesn't matter, right? Did I say to you, did you need to get a heads first or tails second? No, didn't matter, right? So here's the annoying way to think of this one. It is quite annoying. Think about it. I gotta think, how many ways can I get a 5? Would that be just a 10, choose 5? Makes sense, right? Am I done?
No.
Now I gotta go 10, choose 6. 10, choose 7. 10, choose 8. Notice. Inclusive. I've got to count all the possible ways for 5, all the possible ways for 6, all the possible ways for 7. That's why I'm having to do that. And I'm using that fundamental counting rule, but by doing it all, dun, dun, dun. Now, mind you, remember you could have seen this way. 10, choose 5. 10, choose 6. 10, choose 7. 10, choose 8. That's going to be very important to see and remember that whenever we get to 5-1 and 5-2. Okay. Notice when you do your calculator work, you get 252 times, or sorry, plus, and I'm sorry, those are pluses, they're not times, so we're not doing it. We're going to add all the probabilities, my apologies. Because our choose is that fundamental counting number. Remember that? Okay, that choose button does all that fundamental stuff for us. We're just adding things together, okay? Plus 210, plus 120, plus 45, and then we get less. There is 627 different ways for a person to toss a coin 10 times so that the number of tails is between 5 and 8 inclusively. If I said the word exclusive, what would I do to this formula?
Minus 5 and 10, 6 and 7.
Yeah, just get rid of those, right? And then I'm just worried about the 6 and the 7. Okay, so you know what's coming? We're done with chapter 4 completely. We will get through the next class 5-1, and then I will start at 5-2, and then we will start 5-2 next week, and then I will start a review class. Don't forget, March 4th is your midterm. Okay, so I will see you guys later.